Setting alarm limits in vibration analysis using ISO velocity severity zones, defining thresholds for effective machinery monitoring. Setting alarm limits in vibration analysis, introduction to vibration monitoring and alarm philosophy, overview of ISO 10816 and ISO 20816 standards, concept of velocity severity zones, A, B, C, and D, Zone A, new or excellent machine condition, Zone B, acceptable for continuous operation, Zone C, unsatisfactory for long-term operation, Zone D, damage likely and immediate risk, ISO velocity severity chart interpretation, setting alert and danger alarm limits, engineering best practices in alarm management, conclusion and engineering takeaways. Setting alarm limits in vibration analysis is a fundamental engineering task within condition-based maintenance and reliability programs for rotating machinery. Alarm limits act as quantitative decision thresholds that translate raw vibration data into actionable maintenance insights. Without clearly defined alarm limits, vibration monitoring systems risk either missing early-stage faults or generating excessive false alarms that erode confidence in predictive maintenance tools. From an engineering perspective, alarm limits must balance sensitivity and stability, ensuring that genuine mechanical degradation is detected early while normal operational variability is tolerated. Vibration velocity, expressed as RMS values in mm/s or in /s, is widely accepted as a reliable indicator of mechanical stress, particularly for fatigue-related failure mechanisms such as imbalance, misalignment, looseness, and bearing wear. International standards, notably ISO 10816 and its successor ISO 20816, provide a structured framework for interpreting vibration velocity levels by dividing them into severity zones that correspond to machine condition and risk. These zones enable engineers to align alarm thresholds with internationally recognized benchmarks rather than arbitrary site-specific values. In practice, alarm limits are not merely numeric values but part of a broader reliability strategy that includes baseline establishment, trend evaluation, fault diagnostics, and operational context. Effective alarm limit setting requires understanding machine design, operating speed, foundation stiffness, load variability, and historical behavior. Engineering judgment is therefore essential when applying standard limits, as real machines often deviate from idealized conditions assumed in standards. This presentation introduces the ISO velocity severity concept and explains how it is used to define alert and danger alarms in an engineering professional manner, suitable for pumps, motors, compressors, turbines, and other industrial rotating equipment. The objective is to equip engineers and reliability practitioners with a clear, defensible approach to alarm limit setting that supports safe operation, optimized maintenance planning, and long-term asset health. Vibration monitoring is a cornerstone of modern condition monitoring systems and plays a critical role in predictive and proactive maintenance strategies. Rotating machinery inherently generates vibration due to mass distribution, mechanical clearances, and dynamic forces. While some vibration is normal, excessive vibration is often an early indicator of developing faults that can lead to reduced efficiency, accelerated wear, or catastrophic failure. Alarm philosophy defines how vibration measurements are interpreted and how maintenance actions are triggered. In an engineering context, alarms are typically divided into at least two levels: an alert or warning alarm that signals abnormal behavior requiring investigation, and a danger or trip alarm that indicates an unacceptable condition requiring immediate action. The purpose of alarm limits is not to shut down machines unnecessarily, but to provide timely information that allows engineers to intervene before damage escalates. Poorly defined alarms can result in alarm fatigue, unnecessary shutdowns, or, conversely, undetected faults. Therefore, alarm limits must be based on sound engineering principles, supported by standards, and validated through operational experience. Vibration velocity is particularly suitable for alarm setting because it correlates well with the mechanical energy transmitted to machine structures and foundations. Unlike displacement or acceleration alone, velocity provides a balanced sensitivity across a wide frequency range relevant to most industrial machinery faults. Alarm philosophy also emphasizes trending over absolute values, a stable machine operating slightly above guideline limits may be less risky than a rapidly deteriorating machine still below those limits. Consequently, alarm limits should be viewed as decision support tools rather than rigid pass-fail criteria. This slide establishes the conceptual foundation for understanding why alarm limits exist, how they are used in engineering practice, and why standardized approaches such as ISO severity zones are widely adopted in industry. Therefore, alarm limits must be based on sound engineering principles, supported by standards, and validated through operational experience. Vibration velocity is particularly suitable for alarm setting because it correlates well with the mechanical energy transmitted to machine structures and foundations. Unlike displacement or acceleration alone, velocity provides a balanced sensitivity across a wide frequency range relevant to most industrial machinery faults. Alarm philosophy also emphasizes trending over absolute values. A stable machine operating slightly above guideline limits may be less risky than a rapidly deteriorating machine still below those limits. Consequently, alarm limits should be viewed as decision support tools rather than rigid pass-fail criteria. This slide establishes the conceptual foundation for understanding why alarm limits exist, how they are used in engineering practice, and why standardized approaches such as ISO severity zones are widely adopted in industry. The velocity severity zone concept is central to ISO-based vibration evaluation and provides a structured method for interpreting overall vibration levels. The four zones, A, B, C, and D, represent progressively increasing vibration severity and corresponding machine condition. Zone A typically corresponds to very low vibration levels associated with newly commissioned or freshly overhauled machines. Zone B represents vibration levels that are acceptable for long-term continuous operation and are commonly observed in healthy, well-maintained machines. Zone C indicates vibration levels that are considered unsatisfactory for continuous operation, suggesting that corrective actions should be planned to prevent further deterioration. Zone D represents vibration levels that are likely to cause rapid damage and potential failure, requiring immediate intervention. From an engineering standpoint, these zones are not arbitrary but are derived from empirical data, field experience, and an understanding of fatigue mechanisms in rotating machinery. Vibration velocity is particularly effective for defining these zones because it correlates with dynamic forces and stress levels within machine components. The zone boundaries vary depending on machine class and mounting conditions, acknowledging that larger or more flexible machines can tolerate different vibration levels than smaller or rigidly mounted ones. Severity zones provide a visual and intuitive way to communicate machine condition to engineers, operators, and management, facilitating informed decision-making. They also serve as the foundation for setting alert and danger alarm thresholds in vibration monitoring systems. Zone A represents the lowest vibration severity levels defined in ISO velocity standards and is typically associated with new, recently overhauled, or exceptionally well-balanced machines. From an engineering perspective, Zone A serves primarily as a reference condition rather than an operational alarm threshold. Machines operating in this zone exhibit minimal dynamic forces, indicating that rotating and stationary components are well aligned, properly supported, and free from significant defects. Establishing a Zone A baseline is critical during commissioning or post-maintenance acceptance testing, as it provides a benchmark against which future vibration changes can be compared. While continuous operation in Zone A is desirable, it is not always achievable or necessary for all machines, particularly older equipment or machines operating under variable load conditions. Engineers generally do not configure alarms at the Zone A/B boundary because minor operational changes could trigger unnecessary alerts. Instead, Zone A data is used to understand the inherent vibration signature of a healthy machine and to support trend-based analysis. Deviations from Zone A over time can provide early indications of developing issues, even before formal alert thresholds are reached. In this way, Zone A plays a crucial role in proactive maintenance strategies, enabling early detection and root cause analysis while avoiding unnecessary intervention. Zone B defines vibration levels that are considered acceptable for long-term, continuous operation of rotating machinery. Most properly functioning industrial machines operate within this zone for the majority of their service life. From an engineering reliability standpoint, Zone B represents a stable and sustainable operating condition where dynamic forces are present but not excessive enough to cause accelerated wear or fatigue damage. The upper boundary of Zone B, which separates it from Zone C, is particularly important because it is commonly used as the alert or warning alarm threshold in vibration monitoring systems. Crossing this boundary indicates that vibration has increased beyond normal expectations and warrants investigation. However, it does not necessarily require immediate shutdown. Engineers use Zone B alarms to initiate condition assessments, review operating conditions, and plan corrective actions such as balancing, alignment, or lubrication improvements. The intent is to address emerging issues before they progress into more severe conditions. Zone B acknowledges that some level of vibration is inevitable in real-world machinery and that absolute perfection is neither realistic nor necessary. By defining a clear, standardized range for acceptable vibration, Zone B supports rational maintenance decision-making and helps prioritize resources effectively. Zone C represents vibration levels that are considered unsatisfactory for continuous, long-term operation according to ISO standards. Machines operating in this zone are experiencing elevated dynamic forces that increase the risk of accelerated wear, fatigue cracking, and secondary damage to bearings, seals, and foundations. From an engineering perspective, Zone C indicates a degraded condition that should not be ignored. While immediate shutdown may not always be necessary, continued operation without corrective action is likely to result in reduced reliability and increased maintenance costs. The transition into Zone C typically triggers more detailed diagnostic analysis, including spectral analysis, time waveform examination, and inspection of mechanical components. Maintenance planning becomes a priority, with the goal of correcting the underlying fault at the next available opportunity. Engineers must also consider machine criticality, redundancy, and process constraints when deciding how long operation in Zone C can be tolerated. In many vibration programs, the Zone B/C boundary is used as the primary alert alarm, while sustained or rapidly increasing vibration within Zone C escalates the urgency of intervention. Zone C thus serves as a critical decision zone where engineering judgment, risk assessment, and operational realities intersect. Zone D is the highest vibration severity zone defined by ISO standards and represents conditions where significant damage is likely to occur in a short period of time. Machines operating in this zone are subject to extreme dynamic forces that can rapidly propagate existing faults or create new ones, potentially leading to catastrophic failure. From an engineering safety and reliability perspective, Zone D is unacceptable for continued operation except under the most controlled and temporary circumstances. The boundary between Zone C and Zone D is commonly used as the danger or trip alarm threshold in vibration monitoring systems. Exceeding this limit typically requires immediate corrective action, which may include load reduction, controlled shutdown, or emergency maintenance. Operating in Zone D poses risks not only to equipment but also to personnel and surrounding assets, particularly in high-energy machinery such as large motors, compressors, and turbines. Engineers must ensure that Zone D alarms are clearly defined, reliably detected, and integrated into operational procedures. While standards provide guideline values, real-world application requires careful consideration of machine design, failure modes, and consequences. Zone D emphasizes the role of vibration monitoring as a protective measure that supports safe and reliable plant operation. The ISO velocity severity chart is a practical visualization tool that maps overall vibration velocity levels to severity zones for different machine classes and installation types. Interpreting this chart correctly is essential for setting meaningful alarm limits. The chart typically presents vibration velocity on a logarithmic or linear scale, with horizontal bands representing zones A through D. Separate charts or sections apply to different machine categories, such as small machines, medium-sized machines, large machines, and machines on rigid or flexible foundations. Engineers must first identify the correct machine classification before applying zone limits. Misclassification can result in alarm limits that are either too conservative or too permissive. The chart does not account for all operational variables, such as transient conditions, variable speed operation, or process-induced vibration, which reinforces the need for engineering judgment. When used appropriately, the ISO chart provides a standardized starting point for alarm limit definition and facilitates communication across disciplines and organizations. It is most effective when combined with baseline measurements and long-term trending to capture the unique behavior of each machine. The image illustrates a typical ISO 10816 velocity severity chart showing vibration velocity levels divided into zones A, B, C, and D for different classes of rotating machinery, providing a visual reference for alarm limit selection. Setting practical alarm limits using ISO severity zones involves translating guideline boundaries into actionable thresholds within a vibration monitoring system. In most engineering applications, the boundary between Zone B and Zone C is selected as the alert or warning alarm. This threshold signals that vibration has exceeded normal acceptable levels and that investigation is required. The boundary between Zone C and Zone D is typically used as the danger or trip alarm, indicating an unacceptable condition with a high risk of damage. However, these selections should not be applied blindly. Engineers must consider machine criticality, redundancy, safety implications, and historical vibration behavior. In some cases, alert limits may be set slightly below the Zone B/C boundary to provide earlier warning, particularly for critical assets. Conversely, danger limits may be adjusted to avoid nuisance trips while still protecting the machine. Alarm limits should always be validated through trend analysis and periodically reviewed as operating conditions change. Effective alarm setting is an iterative process that combines standards, data, and engineering experience to achieve reliable and meaningful machine protection. Engineering best practices in vibration alarm management emphasize that alarm limits are only one component of an effective condition monitoring program. Absolute vibration values should always be interpreted in the context of trends, operating conditions, and supporting diagnostic information. Engineers should avoid over-reliance on single overall vibration metrics and instead use spectral analysis, time waveforms, and phase measurements to confirm fault mechanisms. Alarm limits must account for changes in speed, load, and process conditions, particularly in variable speed machinery. Documentation and change management are also critical, ensuring that alarm settings are traceable, justified, and reviewed periodically. Training and communication play an important role in ensuring that alarms are understood and acted upon appropriately by operations and maintenance personnel. By integrating ISO-based alarm limits with sound engineering practices, organizations can maximize the value of vibration monitoring while minimizing unnecessary interventions and operational disruptions. In conclusion, ISO velocity severity zones provide a robust and internationally accepted foundation for setting vibration alarm limits in rotating machinery. By categorizing vibration levels into zones A through D, engineers gain a clear framework for assessing machine condition, prioritizing maintenance actions, and managing operational risk. However, standards alone are not sufficient. Effective alarm limit setting requires a combination of ISO guidelines, machine-specific knowledge, baseline data, and ongoing trend analysis. Alert and danger alarms should be selected to support proactive maintenance without causing alarm fatigue or unnecessary shutdowns. Engineering judgment remains essential in adapting standard limits to real-world conditions. When applied thoughtfully, vibration alarm limits become powerful tools that enhance reliability, safety, and asset performance across industrial operations.